So again, today's topic is Python and the RESTful API for high throughput screening purposes. Before we begin, there we go. Before we begin, so the overall focus of this webinar is on the API and how to benefit from using it in the form of running more calculations programmatically. We'll be heavily using the API and exabyte features, so everyone here should be a registered exabyte user. Everyone here at the presentation will receive a PDF of the presentation. It'll also be recorded and made available online on our YouTube page. So if at any point during the presentation a question comes up, please feel free to ask questions using the Zoom tools that we've highlighted below here. And then I always like to start off by talking about the agenda a little bit, what we'll be talking about today. So we'll start off by giving some background information on services in DFT and this idea of a Wulff construction. And then we'll go through calculations with services in DFT, optimizing a unit cell, using PyMatGen to generate services, etc. And then we'll actually use all of these surface energies that we calculate to do a Wulff construction, which gives us a low energy shape for a particle. So we're going to be using surfaces quite a lot today, so it's good to start out with a little bit of background on them. So typically when crystals are introduced like material science courses, typically they're envisioned as this infinitely repeating unit representing a material. But of course, we live in a finite universe, so in the real world, crystals aren't actually infinite and they have to end somewhere. And typically, crystals will actually end up being cut along a plane, which will form their surface. It also turns out that some ways of cutting of the crystal are more stable than others. So over here, I'm illustrating a maybe it's a 101 surface for a just for a simple cubic unit cell, but there's many other different ways that surfaces can be cut. And usually these are illustrated by these things called Miller indices, which sort of describe along which axes are the crystals being cut. The way that we can actually assess which cuts are more favorable is by using the surface energy, which is just how much energy is required to actually form the surface. This is useful also as a descriptor of catalytic activity for some catalysts, and it's also a huge driver in nanoparticle sintering, which is very important to the field of catalyst stability. Surface energies can be calculated using DFT or any other method that gives an energy for that matter for a material. And so what we do when we're calculating a surface energy in DFT is we compare the bulk and slab electronic energies. So over here, for example, I have the bulk cell of copper. Over here, I have a 111 slab. So along the 111 surface of copper, I have this slab over here. And what we do is we can calculate the energy of this bulk cell. We can calculate the energy of the slab. And then we end up scaling the energy of the bulk by the number of atoms in the slab and the number of atoms in the bulk. And then because of computational limitations, typically we'll represent slabs as being two-sided, just because we can't really run calculations in DFT on slabs that are many, very, very, very thick. And so we'll end up actually dividing by 2 to account for the two surfaces here. And then it's customary to divide by the area of the slab's repeating unit, which is up here in this parallelogram. And so that's what these variables mean as I've described them. And then over here, the area, it's actually very easy to calculate of this parallelogram here. We just take the A and B vectors, we take their cross product and then take the magnitude of them, and that'll actually give us the area of this unit cell. And we'll be using this quite a lot later on. Once we have a bunch of surface energies, we can then do something called a Wulff construction, where a Wulff construction actually will give us a size-independent shape that minimizes the total surface energy of a material. Typically, the way these are done is by calculating a bunch of surface energies for a lot of different terminations, and then one can actually do this operation and get a Wulff construction. For example, here we're showing some platinum surface energies from the materials project and their resulting Wulff construction. So this is actually very useful for modeling materials that are larger than a few dozen atoms. especially like at the mesoscale. Oftentimes particles will take on these sorts of shapes. And so it's definitely a very useful concept to have. So because Wulff constructions need surface energies, however, that means we actually end up needing to relax and optimize a bunch of slabs. And because we need to be using slabs, that means we need to be optimizing relaxing unit cells. So that actually gives rise to this sort of flow chart up here that shows the basic recipe of how we can get a Wulff construction. So we start off by choosing the unit cell that's appropriate for our material. We can then optimize this unit cell. We then cleave our slabs to generate a bunch of surfaces. We then run a lot of slab optimizations in parallel to optimize all of those slabs. We can then calculate a lot of surface energies using those slabs. And then finally, once we have our collection of surface energies and surfaces, we can perform the Wulff construction and actually get the particle. So today we're going to be using the API quite a lot and quite heavily to be running all of these calculations. So it's recommended that one is familiar with the API. In the PDF, this will actually be a link to a previous talk where we actually dived quite deeply into the API. But we'll go over a little bit of key points just as review today. So in order to use the API, we need to generate access tokens. And so access tokens come in pairs. So the first one is the account ID, which is analogous to a username, and the second one is an authorization token, which is analogous to a password. And here we demonstrate how to do this. So starting from the home page, we can go to the user profile, click the user account preferences. We can then scroll down a little bit on the account preferences page, and there's this API tokens box. We click generate new token, and then after a few seconds, this will actually pop up with our token information. And so then it's extremely important, by the way, here that we copy the account ID and the username somewhere, because this is only ever shown to users once. And if this is closed, it never gets shown again. So there's only one chance to actually get these credentials when we generate them. So we can copy the account ID, we can copy the authorization token, and then we can go somewhere and just paste them so that we actually have them. So here, for example, we're copying these into the settings.py file that comes with our API example notebooks. And so then they're saved here and we have access to them for later purposes. The way that we use these API tokens is that recalling this pop-up that we had here, on the last slide, so when we're creating a job endpoint, a couple of the arguments that we pass into these endpoint objects when we're making them are the account ID and the authorization token. So account ID, authorization token. There's a few other arguments that we explained in more detail in the API presentation. And so then we take all of these arguments, we can pack them into a list called endpoint args. This isn't necessarily required, but it just makes the code a little bit more compact because we can then unpack this list into the job endpoints objects when we make them. And so that's essentially what we're doing up here. And this is the typical recipe for how we can create any endpoints objects on the platform. We call the endpoint constructor with this unpacked endpoints args list. And so then I would like to briefly go over the parts of the API that we're going to be touching today. So on the next few slides, I've actually highlighted in orange the parts of the API that we'll be using. So material endpoints let us access materials on the platform. Because we're doing a lot of surface calculations, we're of course going to be using this quite heavily. So we're going to be importing from materials project. We're going to be loading local files. We're going to be using material sets, which are essentially folders for materials. We'll be creating, copying, and getting materials from the platform. And again, if we want to access this endpoint, it's just from exabyte API client endpoint materials. We can import this materials endpoint object, which will give us access to all of these features. We're going to be using workflows, which are just reproducible ways that we can run calculations. We'll be actually manipulating workflow JSON today, and then we'll be creating and copying workflows. And again, it's very easy to get this endpoint. It's endpoint.workflows down here, and we can import the workflow endpoints. Excuse me. We'll also be using the jobs endpoint, of course, to set up jobs. And so we won't be using as much of this as is the other ones, but we'll be creating jobs by IDs, we'll be submitting jobs, we'll be listing the files that were created by a job, and we'll be getting the compute parameters to run a job. And so it's also very easy to get a job endpoint. We can just call endpoint.jobs import job endpoints. And finally, just one last word before we jump into things. We're going to be showing off the organization feature quite a lot today. So users can be part of organizations, and that allows users to actually submit calculations under their organization. So here today, for example, I'm a part of the exabyte organization. I'll be submitting all of my calculations to the exabyte organization so that their compute resources are used instead of the resources under my account. They're very useful for collaboration because it allows multiple users to then have a single source where they're creating and submitting jobs and sharing them. And so it's very easy to actually use organizations. Most of the functions here actually accept organization IDs as part of their argument when we're making an API call. And the way that we can actually get this organization ID is easy. We can just go to any job that was run by the organization. So here I'm taking this copper cell opt here. The job ID will be in the title. I then pasted this job ID down below. I created my job endpoint. I called the get function to actually get some JSON from the job. And then inside of the job, there's an owner field, and the owner field has an ID field, and this is the field that actually has the organization ID. And then I can just print it to screen. So here's a little chunk of reusable code that makes it easy to get an organization ID. And so that's what this organization ID thing is going to mean throughout the presentation. All right, so with all that out of the way, we can actually now get into running a copper Wulff construction. So on a copper unit cell. So the first part of our recipe is acquiring a unit cell. We're going to be using the one from materials project here. So over here, there's just a lot of imports up here because I just imported everything all at once today, just so I wouldn't be like importing things later on. So I just go ahead and get the imports out of the way, and then I can actually run a little bit of code to actually get copper from materials project. So I wrote a function here in case I wanted to reuse this. I wrote a function that'll actually, if I give it a formula, it'll give me the lowest energy structure from materials project for a material. So I just, I use PyMatGen to actually create a materials project endpoint. So this is actually run by PyMatGen, not us, but APIs are very common throughout software. So materials project has their own API. I pass in my materials project API key, and this actually spawns this endpoint. I can then call get entries from PyMatGen and actually passing in the formula and a few other arguments. And then that'll actually give me a bunch of copper structures. And the way this is set up is this actually will give me a sorted list of structures, with the first one being the most favorable. So I can just pull the first entry out of the list and then return that as the best structure. And then that's the function. Down here, I'm just saying call this function. And these return PyMatGen objects. So I just get the structure property, which will give me a PyMatGen structure. And then I can also use PyMatGen to get me an ASE atoms object, which are just very, very convenient to work with. Oh, didn't want to do that, which are just very convenient to work with. And so then that actually runs the import. And then I can finally, I can actually end by uploading this to our platform. So I create our material endpoint using that endpoint args thing that I talked about earlier. I can then write the that copper postcard that we got to a file called copper.vasp. I can read the content and then call import from file on that endpoint here. Note that we didn't actually import directly from materials project. That was very deliberate, just to show off the flexibility and there being more than one way we can actually do things with the API here. And so at this point, they're now on our account. And we can start thinking about how we want to actually optimize this cell, because the next step is optimizing this copper unit cell. So again, the cell's from materials project. We'll be using VASP today to run this optimization. And here's some computational info. We'll be running paw potentials with PBE, SEF convergence is 10 to the minus 6 EV, with a force convergence of 0.01 EV per angstrom, 8x8x8 K-point mesh, and then here we allow all parts of the unit cell to relax. So the cell vectors, the cell volume, and the positions are allowed to relax. So translating that to a VASP input, this is what we can get for our in-car and for our K-points files here. And then the next thing that I did was that it's oftentimes useful to not start from scratch and to actually start from something that someone else has made. So I actually went to our platform and I found this variable cell relaxation in the workflow bank. And so I found this, and then I was like, okay, I'll start from here. And so I copied the ID, which is in the URL of this bank workflow. I pasted it down here into the bank workflow ID, and then I could start manipulating this workflow here. And so here again is that bank workflow ID. Over here, I am creating a bank workflow endpoint, and I'm telling the workflow endpoint, go ahead and copy that workflow ID into my organization's account. So this workflow has only one sub workflow and only one unit. That means that I can just pull out of here the sub workflows. There's only one sub workflow, so 0. That'll give me a list of units, or that'll give me the JSON representing the sub workflow. I can then pull out the units here. There's only one unit in that sub workflow, so I can again just pull off the first unit. I can then loop through the inputs of that unit here, and I can say, okay, if the name of the input is in-car, because this was a VASP job, I'll just go ahead and replace the in-car with my in-car, and if it's k-points, I can go ahead and replace the k-points file with my k-points file. I then give the workflow a friendly name. I create a workflow's endpoint here, and I just say, okay, go ahead and create a new workflow. And so that's what this code is doing here when I actually run it. And so it takes a second. And then from here, we now have a setup. We now have the materials. We now have the workflows. The next logical thing to do is to create a job. And so here, I just create a project endpoint here by calling project endpoint with my endpoint args here. And I'm just using this so I can get access to the project ID, because every job on the platform has to run under a project. And so that's all that I'm using this to get. I then create my job endpoint. I give it some compute parameters here. So 4 cores per node. The debug queue, just so it starts quickly. Nodes is going to be 1, 10 minutes, time limit. Even that's probably too much. And then I run this on the AWS cluster. And so then I tell my job endpoint, go ahead and take and translate those compute parameters into something it understands by unpacking those compute parameters. And then I can go ahead and say, okay, endpoint, go ahead and create by IDs. I give it a list, which contains just my cell material, my unit cell. I can give it my workflow ID, project ID, organization ID, a friendly name for the job, and then those compute parameters. And then finally, I can close out by actually submitting the job once that gets set up. And so then that'll actually start the job, and it'll be on our platform. As the job is running, we can of course monitor the job progress. I like watching this because it's mildly entertaining. We actually track the SCF convergence at the top, and we track the ionic energy convergence at the bottom here, so that we can actually monitor our jobs as they're going along, which is oftentimes quite useful to see how far along a calculation has progressed towards convergence. So that'll optimize our unit cell, and then we'll get a relaxed unit cell back. And so then, now that we have a relaxed unit cell, it's time to actually generate our slabs. And so to do that, what we can do is we can actually find the job ID of that copper job we just submitted, which we store in this variable here. And then this is actually a segment of code that we'll be seeing quite a lot going forwards, where I say, go ahead and list files from this job ID. This will give me a list of files and their information. I can then loop through the list of files that the job returns me, and I can say if the name of the file is a concar, I can actually store that file is copper file metadata. So in VASP, VASP actually stores its relaxed cell as the concar file. I can then say, okay, go ahead and get a signed URL for that file here, and I can, by pulling the signed URL field from the copper file metadata, I can then use the URL lib to go ahead and open up that URL. And then finally, I can go ahead and read the URL, write it to disk as a file called copper relaxed VASP. And so then that'll actually write the relaxed unit cell to my disk as this file down here. And so that's what this is doing when we run this code. And so then once that code runs, We can go ahead and actually read this into PyMatGen. We can go ahead and standardize our unit cell here, which is very, very important when whenever we're working with surfaces, because this is really what helps ensure that everyone means the same surfaces. When they say they have the 111 surface, this helps ensure that two people have the same 111 surface by standardizing these unit cells. And then finally, we have this function called get all slabs in terms that we wrote. This will be available in the material utilities on the notebooks that we publish. I've also got this in the supporting slides for this presentation. In the interest of time, we're not going over it, but I'd be happy to show off this code if anyone is interested. Essentially, what this does is this gets every possible slab up to a certain Miller index, and then filters them out for symmetric terminations, and it also looks at every possible termination for each of those slabs. And that's what this function is doing down here. And so this will give me a collection of several copper slabs when I end up running this code here. And then finally, what I can do is I can go ahead and say, okay, I've got these slabs. Let's keep the vacuum size to 15 between repeating units in the Z direction. I can then iterate through all of these Miller indices in my copper slabs. I'm storing these in a dictionary that's of the format of index and then termination and then a bunch of keys. So for the slab key here, that's actually where I'm storing this. I can go ahead and tell the slab to go ahead and center itself about the center of the cell. And then I can figure out a good file name for it here. I'm just calling the file name formula_Miller index_termination.vasp. And I can tell ASC then to go ahead and just write to that file name the slab.
Quick question, James, on the previous slide. What is vacuum measured in? If you go back to the
vacuum here,
slide.
I believe this is measured in, I'll actually go to it. I believe this is being measured in angstroms inside of ASC.
Okay, so 15 is for angstroms.
Yeah, 15 angstrom vacuum between.
Okay,
I believe.
thank you.
And so here is, so once we wrote all these files to the disk, here's actually an overview of what the different surfaces we generated are using this automatic code here. So we have some low index terminations. We have like the 211. Then we have some higher index terminations that we're just looking at because it's useful typically to go up a few different Miller indices. And then finally, we're ending on this 332 stepped surface. So once we have this list of slabs, we can then upload them to the Exabyte platform for further analysis here. And so what we can do is we can start off by actually creating a material set. So material sets on our platform essentially function as folders that help us organize materials into logically grouped things. So here, for example, I'm putting all of these copper slabs into webinar. So we create the material set. I can then loop through all of my slabs. I can say, okay, the file, here's how I wrote the file name. And then I can say, all right, go ahead and open that up, read the file into content, and go ahead and call the API to import from that file content onto the web app. And then once I import the file, I tell it, go ahead and move that into a set. And then I can say, okay, inside of this dictionary, I'm using to track all of these, go ahead and make a new key called material ID that'll actually store the material ID on our platform. And so then we can actually then go to the website just to verify that it did what we wanted it to do. And we can actually see a collection of surfaces and their terminations inside of this webinar Copper Wulff Slabs folder that we created. So now that we have all of these slabs, we're ready to do our surface energy calculations automatically. So here again, we're going to be using VASP. We're going to be using largely the same parameters as the previous optimization of the copper unit cell, except we're only allowing atoms to relax this time. We're going to be looking at a 1-by-1 supercell of these slabs. So just the slab we generated, and then we'll be using an 8x8x1 K-point mesh down here. The one being because in the C direction here, it's very, very large, so we already get a good sampling of K-space from there. So then we could do the same thing that we did for the copper unit cell relaxation, where I went to the platform, I found something close to what I wanted and modified it to suit my needs. Here I found a fixed cell relaxation VASP. I copied its workflow ID into Jupyter Notebook, and I made my in-car, I made my K points. So just like we did with copper, we can go ahead and do that. And then just like we did with copper, I can go ahead and tell our bank workflow endpoint, copy this into my organization account. And again, inside of this workflow as well, there's only one sub workflow and only one unit. So it's very easy to get to the unit we want. So just first set the first sub workflow because it's the only one, first unit in that sub workflow because it's the only one. And then I can loop through the different input files in that unit. If the name's ncar, I can replace it with my ncar. If the name's kpoints, I can replace it with my kpoints. I give the workflow a friendly name, and I tell the endpoint to go ahead and create that workflow. And that's what I'm doing down there when I'm running that. And then what I can do down here in this bit of code is I can actually create our workflow endpoint. And so ignoring this for 1 second, here's my job config down here where I have 60 cores per node. I'm on the OF queue so I can get access to this many cores, up to 12 hours, which is a little overkill for these on the Azure cluster. And then here I'm actually showing off how we can programmatically change the number of nodes we give a calculation. So some of those slabs, as we saw, were quite large. So we might want to give them a couple more cores to actually run a little bit faster. And so that's what I'm doing with these end nodes variable up here, where here I'm just saying, go ahead and take the number of atoms in the surface, divide by 16, round to the nearest digit. That's what this is saying. But then down here I'm saying, wait, this is just for the webinar. I don't actually want to give this too many nodes. For example, a 64 atom slab, this would give me 4 nodes of 16. It's a little bit much. So I said, okay, go ahead and restrict this to be at least 1, but no more than 2. And so that's what that's doing down here. I then tell my endpoint to go ahead and pack all of these compute parameters up. I give the job a friendly prefix. I give it my material ID, workflow ID, and the material. I can then pass all of that into this job endpoint down here, and I can actually create the job when this runs. I then can save the job ID of that surface, and I can into this key right here. And here I just go ahead and immediately submit the job. In contrast to what we did last time, where we kind of submitted the one job after creating it. Here I'm just submitting them as soon as they're made. We can then go online and actually watch the optimization proceed. So this is for that 322 surface, or yeah, this was the 322. So again, these are, I find these enjoyable to watch. Up here, we can actually watch the SCF convergence, and we can watch the ionic energy as the calculation proceeds. So then at this point, once our slab optimization is complete, we're actually ready to do the Wulff construction and collect the slab energies. So that's what we're going to be doing down here. So I start off by doing a little bit of bookkeeping because I need to set up this equation that we've got. So another function that we're going to see inside of that materials utilities file, 1 second. Sorry, excuse me. Another function we'll see inside of that material utilities notebook is actually this get VASP total energy thing that we wrote, where again, the code's available if it's of interest, but in the interest of time, we're not going too deeply into it. Where we pass in the ID of a job, I pass in an endpoint, and it'll actually read the file and extract out the total energy in VASP by doing that. And that'll get us the bulk energy. I can then loop through all of the Miller indices and terminations, and then collect all of the slab energies out by doing the same trick out there. And so then once those complete, I'm actually ready to start calculating the surface energy, which we do down here. So over here, we're just getting all of the variables in this equation is what we're getting in this block of code here. So I iterate through all of the Miller indices, all of the terminations here. I get E slab, E bulk up here in the equation. I get N bulk, N slab up here in the equation. I can then calculate the slab area by doing that trick of taking the norm of the cross product of the two vectors, which this piece of code is doing. It's also available in the supplemental slides if it's of interest, but it's just the cross product it's just the norm of the cross product of these two vectors here. I then print these all out here just so that we're showing our work. And then I can go ahead and call this get surface energy function here, which just implements this formula in Python. And here I'm just being explicit over which variables are which. I can then store the surface energy in this dictionary I'm using to keep track of all of these things. And so then if once I run this block of code, that'll get us that. And then finally, I'm ready to do my Wulff construction. I start off by creating a list of surfaces, a list of energies here. I loop through all of the Miller indices in the slab. I pull out the Miller index into this plain tuple here. I go ahead and append that to the surfaces, and then I go through and I actually find the best energy among the terminations. So here I just loop through the different terminations, and I say, okay, best energy is the minimum we've seen so far, and then I append that to energies out here. And what this does is this gives me a list of surfaces, a list of energies. I can then pass this in actually to ASE. So ASE has a built-in Wulff construction function. Here I just give it a material, I give it the list of surfaces, the list of energies that I made, I give it a size close to what I want. As a guess, I just gave it 147 because that's typically a low energy number of atoms for copper clusters. And then I give it the crystal structure of the system. So in this case, copper, so of course it's FCC. And then I just tell ASE, go ahead and write the Wulff construction to a file. And then finally down here, I can go ahead and just print a list of surfaces and the lowest energy we found for those surfaces out here. Before we dive into the Wulff construction though, it might be useful to actually compare to someone else just to see, did we get reasonable energies for the surfaces? So the lowest energy surface we found was copper 111, which makes sense. Typically 111 is favored by FCC materials. Here's that surface here. And then over here, here's the surface energy we calculated. Here is the surface energy that we found in the literature. And then here's actually the energetic difference between our surface energy and this study that was using similar computational details as us. And we see that we actually are in very good agreement with the literature for these surface energies. So that's really good. That's really promising. And that gives us hope that we actually did the right thing here. It's always good to compare with the literature. And then here's the results of our Wulff construction that was generated in ASE. It's actually the same structure that we were using up here. And here's just a rotating image of it. I actually made this visualization using MolGIF, which is just a really convenient way of actually making these sorts of visualizations. It ends up being 141 atoms as opposed to 147. So it's close to where it's close to where I might expect something of this diameter to be. Now just a little bit of discussion on this Wulff construction we made. So remember how I said that I expected it to be close to 147? So it turns out there's these things called magic numbers for small nanoparticles. They follow the center decosahedral numbers. They go like 13, 55, 147. Typically for small systems, we'll find that that size effects, so like the fact that they're very small actually contribute quite a lot to the geometry they take on. So something of 55, for example, the Wulff construction might not be reasonable. You might instead get a cuboctahedron or an icosahedron. And so size effects are very important for small systems. There's a couple of citations down here that can be referenced to talk about that. Wulff constructions do typically work very well for larger systems, however, once we're out of like a few hundred atoms. So for example, here I cite a literature study that used this technique to actually predict the experimental structure or the experimental morphology of a silver nanocluster that was 6,000 atoms. It also turns out that support effects can dominate. So Wulff constructions don't actually take into account support effects. They are totally gas phase. Typically, clusters will distort a little bit on support. They'll actually compress a little bit towards the surface oftentimes. And then also ligand effects and adsorbates on the clusters can also affect their morphology here. So caveat emptor, Wulff constructions are extremely useful. However, it's very important to take into account other things that are going on with the system instead of taking them to be the end all be all of exactly what the system looks like in operando. And so then finally, I always like to take things a little bit of one step further. We did this with copper. Now let's do this with a catalytically relevant material called γ-Alumina. So γ-Alumina is an extremely important material in catalysis. So it's used as a catalyst and as a catalyst support. As a catalyst, excuse me. Sorry. As a catalyst, it's very useful in something called the Claus process, which is one of the most industrially important ways of producing sulfur. So if we take hydrogen sulfide gas, which we can get from mining or out of natural gas, we can actually pull the sulfur, the elemental sulfur out of that. And this is responsible for making quite a lot of the sulfur. I'm not sure if it's the most important one, but this is like one of the most important ways of making sulfur industrially. It's also found quite a lot of work in the last couple of decades for alkane dehydrogenation on its surface here. It's very useful as a catalyst support just because it can generate interesting support effects at the interface between the catalyst and the actual surface. The exact structure, however, is a little bit controversial just because it's metastable. And so here we'll actually use a very common boehmite derived structure that came from this paper down here. So we took the contents of this paper, we wrote it to a postcar, and then we just called pymatgen to get the structure. And that's what we're going to be doing in this notebook out here. So here again, I just do all of my imports just up front to get them out of the way so I'm not importing things down the road. And then here I just run that same block of code that we showed on the previous slide, and I actually take advantage of ASE's viewer. So ASE actually has this really convenient viewer that lets us actually show the system inside of Jupyter Notebook. And so here I'm just using this just to confirm that the structure looks right, and it looks about right. And so then we've got our unit cell. Then we can go ahead and optimize the unit cell in our platform just like we did before. So here we create our material endpoint. We go ahead and open up this file. We read its contents, and then we upload it to the platform down here. I'm uploading it to my organization, exabyte. And so then that's what this bit of code does. And then we can go ahead and create our workflow here. Here, I'm not modifying the workflow at all. This is that same relax the unit cell workflow that we found on the platform earlier. It's in the workflow bank. I figured that it's probably fine for our purposes, so I just went ahead and used that one. I then copied it to my organizational account, gave it a friendly name, so Alumina Cell Relax, just so we can keep track of which one we used when we're searching through all the workflows. And then finally, I created the job. So here, again, I'm doing this trick to get the project ID for the default project of my organization. I give it the computational info here, so 16 cores on the OFQ on Azure this time for 20 minutes. I can then get the compute parameters and create the job by IDs, just like we did many times before in this presentation. There's not really anything new here. And then finally, we can go ahead and submit the slab or submit the unit cell optimization to the platform. We can then go online and monitor the convergence again. So SCF on top, ionic on the bottom as the job progresses. And then finally, we can go ahead and generate a bunch of slabs using ASE and pymatgen. So here, what I do down here is I go ahead and say, all right, let's get the ID of that job that we wrote. Go ahead and list the files from that endpoint, and we do the same trick that we've also done several times previously, where we loop through all the files that were returned in this list file calls. We pull out the conch car, we get the metadata, and then we pull out the signed URL for it so we can download it. We use URL-lib to actually open up that URL. We then read it, and we can write it to disk as Alumina relaxed. And so then that's what we're doing here. Note, by the way, that we're actually doing write to bytes up here, just because this will actually return a byte string, so we need to write it in byte string mode. And so then, excuse me. And so then we can go ahead and read in the structure with pymatgen, and we can call this get all slabs and terminations function that again we wrote. Here we're actually using an argument called isByLayers. This actually comes out of pymatgen, where pymatgen's slab generator actually lets us specify slabs by thickness or by layers. Here we're actually specifying it by thickness of 3. And so here is actually a visualization of the slabs that we generated here. So we're starting off with the 001 Termo surface, and there's quite a lot. So we're just going to run through these a little bit faster than the copper ones here. So here we have some low index surfaces. Here we also had multiple terminations, which we'll see here, term 0 or term 1, because we're programmers, we start counting at 0. And so then we're just running through these. As we can see, some of these surfaces do actually get to be quite large. In every case, we're showing a, I believe, a 4x4 grid of these surfaces here. And so then that's all of the surfaces that we created. So then once we've created the surfaces, we can just go ahead and upload them to the platform here. So again, creating a material set in my organization, webinar slabs. I can loop through the Miller indices and all of the terminations. I can go ahead and write the slab by coming up with a name for the file, opening the file up from disk, and then just saying, hey, go ahead and import from file. Owner ID is my organization here. And then once I import it, I can go ahead and move it into a materials set. And then that's what this block of code is doing down here. And so that's how we can then get all of these onto the platform. And then just to prove that these really did get to our platform here, I'm going to show off our material designer in our website here, where we can actually, here's one of the slabs. This is the 001 Thermo surface with the name that I gave it. And here we're just rotating around it in the material viewer. So just to summarize, today we learned how to automate the construction and relaxation of slabs, which is a very, very useful tool when investigating any new material. So the example use case here was for the purposes of Wulff Construction, which we find in this copper nanoparticle that we made here. Again, following this recipe here, where the general workflow is we get the unit cell and optimize it, cleave the slabs, optimize them to get a bunch of surface energies, and then using the surface energies, we can get this Wulff Construction, which again is a very useful tool for guessing what nanoparticles might look like. So this is actually a webinar in a recurring series. So the next webinar we're planning to do on the 3rd Friday of next month, where we'll be talking about something else. So please stay tuned. All of the code that we showed in this webinar is actually going to be available on our GitHub in our API examples repo, where the code from this webinar and past webinars can actually be accessed, is Jupyter Notebooks. So we're going to take questions in a second, but if as soon as the webinar ends, a new question comes up, like when getting coffee or something, we are around to answer any questions at info@exabyte.io. So we'd be happy to answer any additional questions there as well. So thank you very much for your attention. We'd be happy to answer any questions at this point.
Great, thank you, James. There was one question inside the Q&A that I already answered. It was about licensing. So the general picture is that we have demonstrated use cases today using VASP, but it can be done using other packages that we support as well. So in order to be able to use VASP, one has to have a license, and one has to obtain it independently today. But the equivalent calculations can be performed with Quantum Espresso using a platform as well. I had a question on your slide number 28.
28. Let's get to 28.
It was about getting the job status.
All right, let's just get over to 28. Here we go. All right, here we're on 28. Right. All right.
Right. When we do submit the jobs, there is a convenient way to get their status and track when they actually get finished. I think we spoke about that in our previous webinar.
Yes, we did. I can actually. Oh, sorry. Go ahead.
Yeah, maybe let's explain a little bit how we can actually track and make sure that all these jobs are finished.
Yeah, so this is one of our API calls. So here, we only used a small subset of these of the API calls that our job endpoint objects know how to do, but it's actually under. Which one was it? It was, I believe it's the get. Yeah, I believe it's get, and then we can actually list, I believe this will return the status of the job as one of the fields inside of the JSON that this returns. Yeah, so in this presentation, because some of these took a while, I just kind of submitted the jobs and walked away. But of course, with this get call, we could then use the status of the job to actually programmatically just run these calculations totally automatically. So for example, here I submitted the cell optimization jobs, and then walked away, got a cup of coffee, and came back, and then manually continued it. But I could have also totally actually had it check this get call for the status of the job, and then just told it wait until the job finishes and then continue for all the slab stuff. We do have some examples of this inside of our API examples on the GitHub, where we actually have a wait for jobs to finish function that actually takes advantage of that. So please feel free to look at that code for more details on exactly how that can be done.
Okay, thanks. Anybody else wants to ask a question? Please raise your hand or type them in the Q&A or in the chat. So far, no questions. Okay, so what we will do is we will follow up with a link to this presentation. We'll upload it to YouTube, share it with everybody. We'll share the PDF, and we will also include a link to the previous webinar to connect the dots. I think previously we spoke about the basics of using the API. Today we looked at the specific example. Next time we're planning to look at analyzing the data that comes from high-throughput calculations and potentially constructing machine learning models. So with that, I'd like to thank everybody, and thank you, James.
Thank you very much. Have an excellent month.
Yep. See you next time.